So welcome to topic 4. In this topic we study simple harmonic motion, waves, we even study light as a wave, and it's a very big unit, one of the biggest that we've done so far. So to start, let's first look at what this studies, right? Simple harmonic motion. Well, simple harmonic motion is a category that studies oscillating or vibrating bodies. So you might wonder what that means. Well, it could be something like a pendulum bob or a mass on a spring. So here's a pendulum, here's a mass on a spring. So a pendulum consists of a string and a bob, like this. A bob is just a ball. Say hi to Bob. Hello, Bob. And if I were to take this bob and pull it over to the side, like here, as is shown, and then let go, it would go back and forth, back and forth. You are getting very sleepy. Okay, or if I were to take this spring and this mass attached to the end, and let's say I pulled this mass down so that the spring was stretched, if I let go, it would want to go back up to the relaxed position. So the spring would go up, and then it would go back down, and it would go up and down, back and forth. These are oscillations, right? Oscillating systems. So before we begin, we're going to do some important terminology review. A cycle is defined as one complete oscillation, right? One whole back and going back. So, excuse me, let me say this without saying back and forth. Here's a cycle for a pendulum. You go over to the left and you come back over to the right. Okay? Here's a cycle for the spring and the mass. You pull it down and you start from down here, so you let go. It goes up and it comes back down. One cycle. We use this term as well in circular motion, and in that context, one cycle is one complete revolution, or one full circle. And of course, a complete revolution is equal to 360 degrees, or in radians, it's 2 pi radians. The zero position. Last year we called this the equilibrium position, and I might slip up and call it that this year, but correct me if I do, unless it's in this video because you can't correct me. But correct me if I do in class. This is not going to be called the equilibrium position because that term is misleading. We'll see why later. So the zero position is the spot where the bob or the spring would remain at rest if not disturbed. So let's say we stretch this spring out, okay? We pull the mass down to stretch it out. It's all stretched out, not very compressed. If you let go, it's going to go back up. So that's not the zero position. Likewise, if you scrunch it all the way up and let go, it's going to fall back down. So that's not the zero position. The zero position is somewhere in between, where if you let go, it just stays there. It remains at rest. For a pendulum, if you pull this thing over and let go, right, it's not going to stay in that position. It's going to swing over. And if you pull it over to the left and you let go, it's going to swing to the right. So that's not the equilibrium position. The equilibrium position is straight vertical, up and down, because if you let go from here, it doesn't move left or right. It just stays there. So an amplitude is this is an important term, and it's simply the maximum displacement from the zero position. Okay? The period, which is also called the time period sometimes, it's the interval of time that it does take, to complete one full cycle. Now frequency is the number of cycles that the pendulum or the bob makes per unit of time. So there's this general form, right? Look only at the left side of this equation and the middle. Ignore this for a second. Frequency is really defined as the number of cycles divided by the time it took for those number of cycles to be completed. Okay. So now, still looking over here in the middle, let's say we plug in one cycle in the numerator, right? Well, what's the time it takes to make one cycle? I don't know, it could be 15 seconds, it could be 8.3 seconds, it could be 0.0004 seconds. But whatever that value is, the time it takes to go one full cycle has a special variable and a special symbol. It's the period. Big T, capital T, is the symbol for period. So we could plug in 1 for the cycles, and we could plug in t for the time, and we get this. Right? Now if we were told it takes 4 seconds to complete 3 cycles, you could plug in 3 on the numerator and 4 in the denominator, 4 seconds in the denominator, and you could also use that to calculate the frequency. But when we plug in 1 and t, that gives us an equation we are familiar with, f equals 1 over t. So that's another special equation we can use to find frequency, 1 over t. Angular frequency. This is another important concept, and it's new to us this year. It's the amount of angle that is swept out in 1 unit of time. Okay? And it's the amount of angle relative to where we consider 360 degrees to be the full cycle. Okay? So imagine we have, and we use this angular frequency not only in simple harmonic motion, but we also use it in circular motion. So let's first consider circular motion. So we have a ball going around in a circle, right? Let's say the ball is at the top, and I measure how long it takes to sweep out 360 degrees, or 2 pi radians. Okay? The angular frequency would be the amount of angle I measure, so 2 pi in this case, divided by the time it takes to make that revolution. But really, I've just defined a specific form of the equation, just like we saw up here, right? You don't have to measure using a full revolution, which is 2 pi, and you don't have to measure using the time period, which is the time it takes to make a full revolution. We can do that, but we could be more general than that, and that's what this equation gives. So, for example, let's say I let the clock run for 2 seconds, and an angle of 36 degrees is swept out. Right? So this thing is going around, and in 2 seconds, 36 degrees is swept out. I could plug in 36 degrees here, and 2 seconds here, and find the angular frequency. Except really, I need to convert this to radians first. Okay. Or I could plug in 2 pi, which is the amount of angle swept out in 1 full cycle t, and that also equals the angular frequency. And if I continue with this equation, we see that 1 over t is equal to the frequency. So now we have another equation, omega equals 2 pi f, for calculating the angular frequency. And this is omega, the Greek letter omega. And it's what we use to represent angular frequency. So here's the trick. If an object has an angular frequency of 2 pi radians per second, then this angle, 2 pi radians, which is 1 complete cycle, occurs in every 1 second. So I want you all to go ahead and solve this practice problem, and we will take a look together in class at this and similar problems. Okay, the restoring force is the nickname that we give to the force, or to the force component, that causes a pendulum to return to the 0 position. So it doesn't just apply to pendulum, it applies to masses on springs and any other example of simple harmonic motion. So let's say we have this 0 position here, and we have stretched this mass down so that the spring is beyond the 0 position. It's not at the 0 position or the relaxed length. If we let go, right, it's going to go up. Here's why it goes up. Weight, of course, pulls down, but there's a force of the spring pulling up when it is when it's stretched past the 0 position. So there's a net force upward, right? A net force upward when the displacement is down below the 0 position. On the other hand, if we push this spring up and compress it, weight pulls down, but now the spring will be pushing the block down as well. It won't be pulling it up like here, because it wants to stretch back out, which means it wants to go down. So now there's a net force downward pushing the spring back down and the mass back down. So if you have a downward displacement from the 0 position, there's an upward net force. if you have an upward displacement from the 0 position, there is a downward net force. So the net force and the displacement always point in opposite directions. Right? What if we have something perfectly at the equilibrium, oh, excuse me, the 0 position? So now the block is at the 0 position. Well, for a spring, and this is not the case for a pendulum, only for a spring, the weight pulls down, and the spring force, the force of the spring pulling up, exactly equals the weight. Right? So this is the 0 position for a vertical spring is simply the position at which the spring force and the weight perfectly cancel. Okay? For a pendulum, here's our pendulum. The restoring force is simply the tilted x component of the weight. So let's say our pendulum is moving out and moving to the left like this. Weight pulls down, tension pulls up, and this weight has an x and a y component. Of course they're tilted, but we see that this is still kind of the x-axis, but tilted, and that's the tilted y. So, for a second, imagine that this wx was not there. Imagine it's not there. If this isn't there, right, then this thing has a leftward velocity, and it has some net force upward, which means it would be in circular motion, and it would just go around in a circle, right? Around, around, around in a circle. But because of this x component of weight, it doesn't keep going in a circle. As it travels upward, it's slowing down because it's accelerating. It's getting pulled back toward the 0 position. Okay. So when we have a leftward displacement, right, to the left from the 0, the restoring force, Wx, pulls back to the right. Now if this thing swings up and then swings back down, at the 0 position, it's moving to the right now because it went over and then back. The weight pulls down and the tension pulls up. Now this thing, this bob, is moving along a circular path. So at this position, the 0 position, if it's moving along a circular path, there has to be an upward net force. Okay? So the tension is bigger than the weight in this picture. That's intentional. It's supposed to be bigger because otherwise this thing wouldn't be going around in a circular path. Okay? But of course there's no x or y component because it's pulling straight down right now at this time, and because there's no angle to the tension. Now if we have the tension over to the side, so we imagine the bob starts here, it goes up a little bit more, it comes back down, and now it's moving over to the right. Weight again pulls down, tension pulls over and leftward, and there's an x and a y component. Okay. So again, tension is going to be bigger than the weight, the y component of the weight. And there is this Wx, the x component of weight, which is the restoring force again. So when the bob is displaced to the left, the restoring force kind of pulls inward to the right. If the bob is displaced to the right, the restoring force pulls in to the left. Wx is left. So again, just like in the previous situation, the displacement and the restoring force always point in opposite directions. So these are some notes on why a pendulum passing through the 0 position is not in equilibrium. And the reason is because it's going to be moving in a circular path. Therefore, it has some net centripetal force pulling upward toward the center of the path. Right? This is true when it's in the vertical position, the 0 position. Now, take these notes. We are going to discuss these, in class. But a pendulum, we know, has its greatest speed when it's at the 0 position. It has a speed of 0 when it's at maximum displacement, because that's where it briefly stops while changing direction. But the mass on a spring, and this is also true for a pendulum, the mass on a spring, right, it feels the greatest force when it's at a position of max displacement, because that's when the spring is most stretched or most compressed. So if the greatest force occurs at maximum displacement, maximum or minimum, then thus the acceleration also does. Okay? And it feels no force when it's at the 0 position, because there is no compression or stretch. So we'll discuss this as well next.